good afternoon. Welcome to the fifth ML4LM webinar. And as one of the main objectives of ML4LM, in today's talk, we are also trying to explore the link and bridge the gap between the physical land modeling and machine learning. And our speaker today is Professor Christoph Rüdiger, who has chosen an appealing title, Physically Based Land Modeling and Machine Learning. What are the complementarities? And I would also, from my side, encourage all the community to try also to define where possible the limit of machine learning in this context. I guess Chris would go through some of them. And to present Chris, so Chris, since July 2024, has been leading the land modeling team at ECMWF, which oversees the continued development of the operational land surface model, ECLand, and is also involved in the machine learning aspect of the land modeling around ECMWF. Prior to that, Chris has been building and leading the then newly formed hydrology modeling team at the Australian Bureau of Meteorology, implementing strategic plan for land surface modeling and stream flow routing. And before that, he was an associate professor at Monash University, teaching hydrology and groundwater courses, and leading research on land surface modeling, data assimilation, and Earth observation. Chris has also a strong observational and field campaign experience through conducting calibration and validation campaign across Australia for the ESA's MOS mission and the NASA's MAP soil moisture missions. And with that, I would like to thank Christoph for agreeing to give this presentation. And over to you, Christoph.
Thank you, Sohail, and thanks for everyone who's online around the world to spend an hour with me talking about land modeling and machine learning, really. So I'm going to present the presentation results, let's put it that way, not from me. They are coming out of the team, very talented team of 10 people in the land modeling team, but also in collaboration with other teams throughout ECMWF. So where people are acknowledged that it's their work, and I'm hoping that I'm not saying anything wrong about what they've done. So what this presentation will contain is more or less a philosophical travel also through time, or at a philosophical reflection about what we see as in land modeling and machine learning, and how we can explore the complementarities between them all. Throughout, I will be quoting, and often not misquoting, but quoting out of context, famous people at times or other people. And the reason is that the quotes are out of context at times is because it's what we're doing with modeling and machine learning is also not an exact science in that sense. We also have made assumptions and their limitations in what we can do or what we are doing. When I started thinking about what to present, and I had gone through my first iteration of the presentation, I felt that I had to take a step back in time and really go through the history of land modeling briefly. As you will see throughout the presentation, I feel it's important to make that point. So the history of land surface modeling as such within a coupled context is about 60 years old. So in the 60s, the first models for climate studies were being conceived, and Manabe was really the first one to set up a fully coupled model, more or less. So the representation of the land was fairly simplistic. So it had a fixed soil depth and global parameters that were not spatially varying. There was a saturation excess runoff only, no heat conductivity into the soil, and the evaporation was limited by a certain water threshold. So it's a very simplistic representation of the Earth because of the land surface, sorry, because it was only meant to be a boundary condition to the atmosphere, really. Over the years, or over the decades, into the 70s and 80s, land surface models became more complex, and we started having layers of soils. We may have started seeing vegetation and other surface processes like surface runoff, snow accumulation, and others. These days, we have usually semi-distributed models that are usually gridded in one way or the other, be it a regular or irregular grid. They're global models. They're running often with spatially varying parameters, but they're usually linked to a certain type of vegetation. And we often only have a dozen or so vegetation types that, if you were to take the same tree species in California or in Australia, they would have the same parameters. So there would not be hardly any recognition of adaptation in the models in general, in the operational models. The tiles, the surfaces are usually tiled, but not the subsurfaces. So that means that we have land cover that varies across space, but unfortunately, subtiling soil underneath is a fairly demanding task, and we are in operational centers, we usually don't do that. And also those soils, so those pixel columns are independent. So we're running each pixel vertically by itself. There's usually not an exchange of water or energy between the soil columns. So these days, when you look into ECLand, where ECLand sits within the integrated forecasting system here at ECMWF, you see that it's become a fairly complex system of different modules that form the model and that interact with each other in various ways. So it's fairly complex, and it can have switches to go on and off. So it makes it a system that is not easy to understand at times. So just to summarize where the development of land surface models over time, Fisher and Coven have created this interesting plot. So as you can see, this on the left-hand side, the 60s and 70s, so really just a boundary condition in the land surface until we started in the late 70s and early 80s to add vegetation, soil moisture, and throughout the years or decades, other parts of the models. So, and also all the way to the point that we now have crops and irrigations or lateral flows in some of the models included. So the capabilities are there. Also the computational resources have significantly increased, but more importantly, the observations. So we have much more data available that allowed us to further develop the land surface model. So to say that in the last 40 years, let's not go back to the 60s or 70s, in the last 40 years we have come a long way in land surface modeling. It has become more representative of what's happening on the land globally. But there are still a lot of processes under investigation. We have snow, urban, vegetation, soil, water, and then the coupling with the atmosphere. There are a lot of aspects that are simplified in their models or are not represented at all because they may not have the significant impact on the atmosphere that would allow us or justify us to really incorporate them at the moment. So looking at how complex the model has become, or how complex actually more so the land surface is when you look into it, there's the land surface model paradigm. So if you go to an increasing resolution, and you can see here it's the power of -1, so going to the right, you have a higher and higher resolution of the model. You can start seeing a resolved complexity, or you have to include more and more model processes. So in reality, and I'm telling you in a moment why reality is here in apostrophes, or quotation marks, the higher the resolution, the more of the processes you're resolving. It's like stepping back into space, looking at Earth, you see a few green blobs, but you don't see the trees. But you get closer and closer, you see the trees. You get closer to the trees, you see the leaves, and you get closer to the leaves, you see the stomata. In the soil, it's similar. But the thing is that the land surface models were only designed for large scale, or initially they were only designed for large scale processes being part of an operational model. So the operational land surface models have somehow reached some sort of a saturation in terms of the complexity that they can resolve, because a lot of the processes we have are just made to be lumped processes within a tile, or in a way simplified as well across scales. Therefore, we also only have effective parameters often, because we're just smearing out the information across a larger extent. So to visualize that, I've taken these
Chris, can I
Yep.
interrupt you for a second? Because your screen has shifted to the left, and not all of the figure are shown. So
okay.
if you could.
So hang on, I may have to reshare them. When did it happen with the shift to the left?
I'm not sure. Actually, it's the last two slides, I think.
Okay. Well.
And in meantime, I would encourage people to send the question through the Q&A section and not the chat one. Thank you. Okay, that looks much better now. Christoph, please go ahead.
Okay. All right. Thanks for letting me know. So as I said, you have the high resolution, and I was already with the images here. So what you see here is actually a microwave image, but the resolution is 25 kilometer. So basically that's what in the past decade the land surface resolution was within an operational center, of course with the tiling that we don't see here at the moment. What you see here looks like a lake and some other features that you can barely decipher. Now, if we go and take another Earth observation system, you can see totally different structures around here. This is the same area. You can see the black boxes here as reference. This is Lake Eyre. This is actually in Central Australia. This is a salt lake. You see those plains here. Those are not mountain ranges, by the way. Those are rocky plains, and the desert here. So you see features that are actually you don't see in the lower resolution. And that's what I mean with the land surface model paradigm and the problems that we have resolving complexity. You can also then go, even though this is 1 kilometer, you can go higher resolution and go higher and higher and higher. You will always increase and introduce new complexity and new processes that you would have to consider at some point. So there's also logic behind not going further, because some of these processes are not well understood at times. So if you look into one of those pixels and you see all the difference in the land cover type and the orography and things like that, and compare it to how the model often sees it, you have a very strong simplification. You've got your river system here, to which areas are being drained. You've got a simplified surface and a simplified water table in there somewhere, or saturated and unsaturated zones. How this is distinguished is often with very simple equations like this one here, where the fraction between, or the fraction of saturated of the total slope is calculated through some sort of a shape parameter here in the power function, and the relationship of the current soil moisture state over the saturated soil moisture state. They look very dissimilar. So very different, but we assume that this one is doing basically the right thing. So it also shows that we need to start thinking a little bit differently about how we represent the lens surface within a model. So that's also why people have started thinking about machine learning for and with lens surface models. So it started way back with a paper that really started exploring machine learning within a parametric lens surface model. And in recent years, there have been so many papers that have come out that we have had review papers writing about what the recent developments over the last 10 years in that field were. And one of the most famous ones are, of course, the work that the papers that have been done as part of Google global flood monitoring system, where they've developed a rainfall runoff model using long short-term memory system networks to predict floods. And because of that, there's more and more the interest in using machine learning. So, but if you look into it, even Google, this is the Google Flood Hub, has large gaps. And if you zoom in, there are even more gaps. This is because this is purely observational and data driven. So what you need are in situ observations. And of course, you don't have those observations all over the world. For example, here in France, you don't see, well, the whole Seine basin and the surrounding region of the Normandy and below, where almost a quarter of the French population live, or a bit more, don't have any observations and therefore fall outside of that system. Also, in terms of spatial complexity, what you see here is one of those intermittent flowing river networks in central Australia. It only flows when the monsoon or cyclones hit here in northern Australia in the summer period and inject enough water for those rivers to flow. So each pixel here is 1.5 kilometers. So the waterfront that you see coming here is roughly in the order of 15 to 20 kilometers wide across various pixels of your lens surface model and your routing model, but there are no observations. So that means machine learning can't actually do anything with purely observed driven model, observations on data. That means that, well, we have gaps also in machine learning. So the machine learning is not the only solution. But then we also have identified that we're having problems with the representation of the lens surface through the lens surface models. Another problem is this assumption of stationarity when you learn from the history. And here's one of my misquotes. History will teach us nothing. So Hegel never said that. It was just a modification over the hundreds of, well, from the 18th century when he wrote it to us. He basically said in the political framework is people don't learn much from the past because we're constrained in the here and now by the situation we're finding ourselves in, and the future may be different. And that's the same, very similar to lens surface modeling or Earth system modeling. We can learn from the past, but by nature is changing and shifting. And therefore, we need to think about, if we learn only from the past, can we really predict the future? And when you look into this here, this is a study about streamflow extremes, where you can see it was fairly stable for about 30 or 40 years. This is a river in Australia. But suddenly, with the millennium drought that happened in the late 20th century and into the first decade of this century, things had shifted. So the catchment response had changed. So what are we doing if we had learned only on the data that we collected before the year 2000? The system or the observations had never seen those conditions here. So it means I'm not saying we should not look back into the history, into the past to learn for the future, but it also means that we need to be agile and adaptive enough to adapt along the way or find a solution so that we can learn from the past, but also include our understanding of the physics and how they change into the future. So predicting the future from the past is tricky because it's more often done with regression models. So especially if you do it on past data, depending on which sort of regression you use, it looks different. And when you look into frequency for analysis, for example, you're fairly good, those are the uncertainty envelopes here. You're fairly close to your observations, your observation space when you have a lot of observations available, but that envelope becomes fairly large when you have fewer and fewer observations, and this is not even a 1 in 100-year event up here. You already have a fairly wide spread of the possible scenarios, statistically speaking. So how do we know that we actually, our observations are actually what are representing what we see or what we expect into the future? Do we have enough observations, for example, at hand to represent the whole range of possibilities? Then we are also limited by other observations. That is, land surface models require ancillary data or climate fields or whatever you call them. In terms of, for example, here on the left, you see the soil maps, soil map of Europe. It's fairly complex. I've done field experiments in the field. We needed to take 3 measurements within 30 centimeters to average the soil moisture measurement, because within 30 centimeters you can get a different measurement. So how do we present all that? Other people might say, oh, well, we have satellites and we can observe what's happening. Yeah, but with satellites, we can only observe what's in the top 2 to 5 centimeters if we're lucky. We don't see what's underneath. We don't see the structure of the soil. We don't see where the roots grow. We don't see where the water goes or how it infiltrates vertically. We need to model it one way or the other. So the thing is, and I want to ask you as well to think about that, are we asking the right questions? So another paper coming from Google, and I'm not saying that I disagree with Google, they're doing a great job. But I would turn that question around that they posed here for the paper, where they said, what role does hydrological sciences play in the age of machine learning? I would ask for rather saying, what is actually machine learning? What can the machine learning age do to our capabilities of modeling? Because it's not easy to merge the two in land surface modeling, so especially not if we want to do data simulation, for example. So the thing is, and I want to talk about that a little bit more now, is how can we make use of machine learning actually to improve our models? Because the better our models become, the better the training data set will be that the machine learning models require to do the projections into the future, or the forecasts. So coming back to that slide that I showed you before, and let's say we are here and we want to improve the resolution. So that means we have this gap here between the land surface model and our whatever we want to see as a reality. Because our reality in that sense depends on the scale we are working in. So we are basically at a situation now with land surface modeling that we can say we have come a long way, but what now? Because in order to get over this wall and onto this lush green surface here with all these other targets that we want to address, how do we get actually up there? So going back again in time is now the earliest rainfall runoff models were simple bucket models. So you had some sort of soil moisture within the soil, you have precipitation, water goes in, you have evapotranspiration that removes water into the atmosphere, and you have 2 runoff components, either on the surface and the subsurface when the soil gets close to saturation. So it means you can write this problem as a very simplistic equation. So it means the current state is dependent of the conditions of the previous state, plus and minus your input and output. If we were to take the surface, we can write it like this. So the precipitation minus the runoff, we can say that's 1 minus some sort of parameter times my total precipitation, because the surface runoff is a function of basically how much water is falling. So let's call it the runoff coefficient. And we take the other two components that are then as a function of the soil moisture, because evapotranspiration is a function of it, and the subsurface runoff as well. So we can also say, well, those two losses, why don't we put a parameter m to it? So basically our equation becomes this. So we suddenly have our current state, which is a function of the previous state and some sort of input times something. So we can formulate it like this. If you disagree, you can shout out later to me. But it's a fair simplification of the problem. So if we take Frederick Kratzat's paper, so he works at Google nowadays, and you compare the state update of the LSTM with the state update of the bucket model, what's the difference? So at this point in time, I could say there's actually no complementarity because the two are the same. Why should we bother going on? But it would be too superficial, because the difference here is those are calibrated parameters, very simple ones that only look into the balance. I stole that idea actually from Frederick Kratzat's talk at the EGU 2 weeks ago when he was talking about his work. And one of the things that he mentioned here was when they did the first runs, they realized eventually that they had actually also learned something about the snow, something that with a bucket model you wouldn't do. But here there was information content in the machine learning approach that could be used also for other applications and also to improve what they were doing. So it's really those opportunistic at times findings that can help us. And it shows that there's information in the machine learning that we can potentially use to improve our models. So, and to do one of my quotes here in this case, Isaac Asimov once said something along the lines that the most quoted phrase in science is not "Eureka, I have found it," but "that's funny." And I think we are onto something here, and we need to further explore. So the way that we are taking now here at ECMWF in particular is that traditionally we have had a parameter space P. We had observations at the land surface. We calibrated the land surface model. Physical-based optimizations locally worked well. Globally worked okay. But now we have other opportunities as well. We can generate emulators. We can use ML and AI approaches to optimize our parameter spaces through machine learning. And the third one is we can also then go and do, well, for example, what the Deutsche Wetterdienst is doing, that you have regular daily updates of your parameter space. So those are two or three totally different approaches. One is physical, one is machine learned, which represents more the overall system behavior, and the other one is pure optimization. I don't care about the land surface, I care about what the atmosphere is giving me, essentially. So they're based on different assumptions and philosophies behind it. One is, as I said, the physical modeling can be used for the physical model development. The other one for emulators to facilitate the running, making it cheaper potentially to run. And the other one is for very short-term forecasts, because those optimized parameter spaces are only valid for a short period, and then because of the dynamic nature of the system, they become less and less accurate. So, but if we go and use the information, interchange the information flow between the three aspects, we should be able to make use of those. We should be able to improve all three of them together. And that's the thing that we really want to look into now. So at the moment, what we're doing in ECMWF, ECLand is our land surface model, and we have created something that's called AI Land. So we're really acknowledging Nina Ho's work here. And if we're looking into how long it takes to run the model for a year, so for about 4 hours at 30 kilometer resolution with a limited amount of CPUs, it's not that expensive. So we've tested different types of machine learning approaches, and we've found some benefits and so pros and cons between the different approaches. And at the moment, we're mostly working with the multi-layer perceptron, but I'm not going into the details here. It's not my space really. And we've also, what happened here at ECMWF is the NMOI framework has been developed that simplifies the handling and the pre-processing of the data, especially for machine learning training purposes. So what we are seeing here is, while in the first epoch, for example, we have not so good distributions of our target variables, after a while we find actually that a lot of those variables or parameter spaces we can cover fairly well. As an example, what we've done so far is the learning the roots on soil moisture. So there for us, it's currently the level 3, so that's below 25 centimeters depth. And what you see on the first one is a difference, sort of average differences, biases in most of the areas, and then the tropics a bit of a stronger one. After a few epochs of iterations, those arrows have largely disappeared, and the scale here is actually very different, so be mindful of that one. The patterns are fairly similar, so you still see some issues over the tropics. This is usually due to the dense vegetation, lack of observations, topographic complexity and things like that. But we seem to be on a good track with AI Land to learn, but it has only learned from past models. So it can replicate ERA 5 really well, but we don't know what it will do into the future. So in order to stabilize or to provide a better learning background for the AI model, you can also train it rather than training it globally. You would train it on different regions and then transfer that knowledge or that training data set to different regions. And what you can see here is for AI Land trained on the Sahel region and running it, I think it was for Europe, sorry. The soil moisture looks reasonably good at the top layer. Soil temperature, well, we see the patterns, but there's a bit of a drift at times. And interestingly, we see snow. Despite the fact that it was trained on the Sahel, we see snow. Well, there are a few patches of snow if you take a larger cross-section of Africa, and this can be part of that one. But it shows that transferring knowledge, you also have to be mindful when you do that with machine learning approaches, because the knowledge may not be representative of where you're transferring the model to. If you apply the learned approach, the learned model of the boreal region, you have an underestimation of the temperature, just because the model expects different solar zenith angles and things like that. However, the snow is much better, I have to say. So one of the things is, yes, we can simulate the variables reasonably well, but we also wanted to see what happens if you permit or if we change the parameters, for example. Do we see a response in the AI? And we do. So in this case, the field capacity was changed as a parameter in the AI model, and you can clearly see changes. So here is a half of the value, and it really pulls down the possible simulated soil moisture. If we were to increase it, it goes up. So that's promising, because in that case, we know that we can work with parameters within the trained models. That means we can use those models to optimize our parameters. For example, if we were to take our models and then be able to have a much broader space, we can then also run different permutations of the parameters and in a much bigger parameter space and try to extract try to use the machine learning system to extract much more information out of it, rather than going the traditional way where we calibrated one parameter because we had the point observations at hand from a field site, or worse, of a laboratory experiment. We could even push that further, and I'm not going into the details here for that one, but the questions could also be, can we exploit the differentiability of AI land for land data assimilation, because that's important for it. And that would allow us to actually run a machine learning model and do a simulation into it using satellite observations. Other approaches, and we're going now to Birgit's work, is the optimization of parameters using an emulator of the land, also combined with a Bayesian multiparameter approach. And you can see here that the more iterations we have, the closer we come to an optimized value. We could go into far more detail for that one, but I'll show you some results of the approach. So in this case, we've optimized the orographic fields, or better parameters, by sampling various simulations. In this case, 200 simulations at a given resolution. You can see here the spaces. Purple is an increased error, yellow is further and further reduced error in the simulations, and therefore our optimized parameter should be somewhere here. But if we combine it with the others, we find different combinations of optimized parameters. Due to time, I'm just hurrying up a little bit, but what you can see here, if we use this approach and optimize our orographic fields within the land surface model, and when we then look into the forecast of the 10-meter zonal winds, we see significant improvements in certain regions, especially here along the Andes, in the Himalayas, and other regions, especially where you have high level of relief. Another approach that we've taken is the adaptive parameter tuning that I mentioned before. It was the third bit to see how the day-to-day tuning of our parameters can improve our forecast. And what you can see here is for a month in June 22, the Southern Hemisphere doesn't see much of an improvement. Sorry, it's an optimization of the RS min value here. What we see here is the Southern Hemisphere, not so much, could be for various reasons. We've just created those results, so we're not quite there yet with the interpretation, but it could well be also that this is winter period in the Southern Hemisphere. For the tropics, we see a significant improvement in the normalized, reduction in the normalized error here, using this approach of the adaptive parameter tuning. And we also see a positive impact over for almost a week in the Northern Hemisphere. And when you look into it across the atmosphere, you look into the 12-hour forecast, you see certain regions, especially here in the tropics and the subtropics, significant improvements, and here in the boreal regions as well. You see some degradation of the forecasts across time. We still have to investigate what those are, but this latitude is, for example, also the same as large parts of the Himalayas. So it could well be that tuning a parameter globally is not improving it everywhere, but certainly you'll have some degradations here and there. So the question is then, what can we do to improve that approach? And what we've done is we've now clustered the land surface into 30 different clusters. So that means clustering it according to vegetation, soil, climate regimes, just to make sure that what we have are zones that are very similar to each other. So that reduces the need to have point-wise calibrations, which would blow up computational cost. And in that way, we can find optimized parameters for the regions, for the clustering of the regions. And so that's where we are at the moment, and hopefully in the next few weeks we will find out whether this is the right approach. So I've spoken a lot about what we can do with machine learning for the model development, or what we do with machine learning in order to simulate the model eventually. But machine learning can also be used in applications, and this is also where a big benefit is. So ECMWF has what is called the probability of fire. So that's basically what's in the black box here. Is what we've done, or Joey has done, is he's used a lot of the model output and also satellite observations to train a model to predict the probability of fires per pixel. This is then later linked to a fire spread model, which I'm not going to go into detail about. So what Prof does is it takes a lot of model data, but also ancillary information together with satellite data on active fires in the past. And through XGBoost develops a probabilistic forecast of fire risks. So what comes out of that one is then a map, a global map of probability of fire, which you can see, it makes sense. There's the Sahel region, it says Southern Africa or the Amazon, you've got Australia. When you look then into, for the same period of this forecast, the number of days that MODIS has actually observed fires, you see a strong similarity, which is very promising. To zoom in a bit more closely and to look into the extreme fires of Australia in the late 2019s, early 20s, and looking at the forecast of Prof for specifically for the 15th of December, you see all these active fires here. You see what the traditional system was outputting. This is Central Australia. There's not much vegetation, so there's spinifex fire. So those are bushes that can burn fairly substantially. But there's not much here on the coast, but you see all those fires on the coast. So Prof with XGBoost was actually predicting a lot of those, the likelihood of those fires fairly well. Using only the same framework, but only using climatological data, so only static, annually repeating data, the probability of the fire was much lower and way off, essentially. Zooming in and comparing it against the remotely sensed map of all the fires in the region over those 5-6 months in southeastern Australia, you can see for this specific date, so this is again the forecast here on the right hand side for the 15th of September, you see is a lot of those fires around Sydney here as well, that actually were well predicted by the system. You could say now that, oh, but what about here in the southern corner here that didn't predict it really well? Well, the thing is that this area burned 2 weeks later, so that was the next forecasting cycle. And this is, it burned on the 31st of December and not on the 15th or by the 15th of December. So we have come a long way. I can only repeat it. And also now over the last year or two, we've come also a long way with machine learning. So that means the machine learning may actually provide us with the steps to get up to this level here. How we navigate all those new challenges is then a different thing. Do we have reason to celebrate? Well, we have reason to be happy that we're where we've come, but don't get complacent. We still have a few steps to take. So, coming slowly to the end of my presentation, I wanted to give you 4 questions, a little bit of food for thought, because in terms of what ML can do to help us land surface modelers with. And I'm quoting there from George Kucera, who was working on parameter optimization, and he had those known knowns and so on and so forth. You see them. So I'm quoting him out of context, but I think it fits here really well. So we've got the known knowns. So basically so much that we know that we have them in the model. How well do we actually know those? Can machine learning help us to quantify the quality of our models? then there may be the known unknowns. Where do we get this information from? So the known unknowns are where we know that there's some process, but we haven't included it into the model. Can we use machine learning to first test what the impact would be to include those into the model? Next step is then the unknown unknowns. So is there something obvious that we actually know, but we haven't included because we haven't thought about it? Can machine learning point out processes that are lacking, for example, or areas spatially on the globe where we see issues, and we may start thinking about, maybe we bring in this process here, and maybe that's what's missing because of plant physiology or soil physics or other aspects on the land surface. And then there are the most tricky ones, the unknown unknowns. Those are the ones we don't even know about that they are missing or that they are out there. How do we find out what those are? And are they relevant? And if they are relevant, how relevant would they be? So this is just blue sky research, but this is the most challenging and intriguing question, really, in my opinion. So coming to the conclusions, what do we do now? So looking back at what I've presented and what I think we need to do is, I think we need to change how we do land surface modeling. It's not that we're going to get rid of the physical modeling. We will always need the physical modeling. As I said before, we need physical modeling to improve our training data set for the machine learning, because we can't observe what's in the ground underneath. So we need to improve the models. But we also need to improve the models in new ways. We need to exploit more or make use of what machine learning can offer us. The question is then, you can ask, but how? How do we do it? First of all, we need to use more observations. There are a lot of in situ observations. There's a lot of satellite data available. We just need to make use of it in a more intelligent way also. So the thing is that the value of machine learning for land modeling is not in the computational time. Land surface models compared to an atmospheric model are reasonably cheap. We need to really exploit the added value that machine learning can give us, like what I have said about what Frederik Kratzer found in his first runs, that he learned about snow without even intending it to do. And don't fear if you're a physical modeler. I don't think that will be made obsolete because of the long-term aspects, because of the non-stationarity and the chaotic system of nature and the Earth system by itself. So what is actually the risk if we continue on this pathway? And there's definitely a thin line between physically meaningful parameters and just tuned parameters. If we're going back to, we just need to tune the land surface and we don't care about it, as in the 1960s or 70s, we are going the wrong way because we need the land surface. There are so many applications on the land surface that rely on it. I had a little sign there on the green grass. It says disasters. Disasters are only where people are. Otherwise, it's a natural event. We need to model that. And people are on the land surface or on the ocean for that matter. Not many of us fly constantly in the sky. The other risk is that we may not have enough data available, real observed data. So we need to really, that's why I come back to that, we need to make a more intelligent use of the data. Otherwise, we won't be able to exploit that data set. So at the end, some cynics may ask, do we really have to do it? I think the short answer is yes, because there are so many opportunities hidden in machine learning in combination with land surface model that we would be quite stupid to ignore it. But nature is nature. Nature is chaotic. We can't simply rely only on data. We need to go out there and still understand that there's so much we don't know yet, and there's so much to do. And with that, that's the end of my presentation. Thank you.
Thank you very much, Christoph, for this very comprehensive presentation and triggering a lot of questions. So I would encourage the attendees to go through the Q&A and ask questions. And in meantime, I have a simple one. So you mentioned the data and the in conjunction with the representativity issue that machine learning could have when we have not enough data. So what about the usefulness of the satellite data in this context?
It depends what sort of satellite data you're using. I mean, for example, soil moisture measurements, as I said, it's only the microwave measurements only penetrate a few centimeters in the soil. But then vegetation can also be observed. So, for example, the fluorescence of the vegetation is strongly linked to the health and the activity of the vegetation. And that is largely controlled also by the soil moisture in the root zone, which we cannot observe directly. But we could draw conclusions on the subsurface soil moisture using the vegetation response over time. And that's what I meant with we may have to use data more intelligently. So we have to see beyond the primary purpose of the data, be more opportunistic in the use of data.
Okay. And you have a first question from Elizabeth Lewis. Do you want to read it, or I can read it for you? Yeah, please go ahead.
Open the window. All right, so the question is, have you come across any good methods for physics discovery from machine models? That means methods for identifying the unknown knowns and the unknown unknowns. Frankly, no. That's the tricky bit. It's really, that's why I've put it out there. We all need to work together to make that happen. And then another question by Jacopo. Perhaps I missed that Anemo is a graph-based framework. Which model are you using for training the emulator LSTM transformer? It's the perceptron. At the moment, we tried a lot of them, and I believe at the moment we've settled for the AI land on the perceptron.
Okay, I have another one, Christoph. So again, on the representativity issue, but also then in time for this question. So in this changing climate, but also when we have anthropogenic impact, how do you think machine learning could help there?
Well, it's two-faceted. One aspect is that machine learning could simulate the anthropogenic behavior that influences the land surface states. That's one aspect. The other thing is, for example, with reservoirs, we could have altimetry observations in combination with the routing scheme, trying to learn the release parameters for the water from the reservoir. Something that is driven by managerial decisions and not by physics. And maybe there are patterns in there that we don't see, hydrologists and our land surface modelers in general, so that we can improve the model and sort of automate the release mechanisms within the routing scheme. Just two examples.
Okay, thank you very much, Christoph. I think if there is no more question, then we could. No, there is two more actually. Yeah.
So how would a land surface model look like according to you? Well, it's going to be some form of hybrid approach, definitely. My view, and that's my personal view, is that we may replace processes that we've defined as physical within the model. And if we don't know anything about the physics or the behavior of the model, or the parameters that we require because we can't observe it, we may just as well replace it with machine learned modules, because then it cuts down on the computational time. The other aspect is that definitely with the parameterization. So they will have to go hand in hand. Maybe and it depends then also on the purpose of the application. So for us, if you look into the short-term or medium-term forecasts, you may just go with the adaptive tuning, because your target is to get the atmosphere right. But if you have an application, then like the fires, or like Google is doing with a runoff, with a streamflow modeling, you may go and have specific applications that are almost purely based on machine learning, but have learned from the physics models. So it's going to be a hybrid physical machine learning approach, and we need to improve the communication between the two. So the next one is, I have a question about known unknowns. How can we ensure that the physical laws that we derive from machine learning are flexible enough for the changing nature? No, we can't. We don't know what nature will look like in the future. So we can only make assumptions, really. But we can improve the model's representation of what our understanding of the physics are right now. With vegetation, for example, we can improve how vegetation adapts to climate change in the background. All those types of models do exist. We just need to make sure that they're working well. But who knows what the vegetation, what a plant is doing with 50% more CO2 in the atmosphere, whether it saturates or not, we don't know. How can we avoid good results for wrong reasons? Well, we need to be diligent. We need to make sure that we do our homework, that we double check, that we do understand why we get to that point. If we don't understand, we need to flag saying, whoa, this is a black box. And therefore the results look good, but we're not sure that we've actually come to this for the right reasons. And that's what I meant with the land surface models in the 60s and 70s. There were boundary conditions. When I started my PhD in the early 2000s, I saw wet deserts because the atmospheric model needed water in that area. So basically, so do your homework and try to understand what actually comes out of it, and not only throw it on the market and say, yeah, look at my results. Okay. So I understand the question previously was from Francesca. Good.
Yeah, I have a last question probably because we are on time. It's more an opinion than to see whether you agree for it. In the next decade, let's say, can we say that machine learning for land cannot live without land modeling, and also land modeling cannot live without machine learning?
No, I wouldn't say cannot. I would say we need to live, to come together. We need to make the journey together, because alone, neither of them will be good. Neither of them will improve and make us future-proof.
Yeah, that's what I meant.
Value is in both.
Live without one of the other, yeah. Okay. Thank you very much, Christoph, and for all the attendees. It was a very nice presentation, and I would like to remind that this presentation recording will be on the ML4LM page, as well as the slides. And see you on the next webinar. Thank you very much.